and I don't know whether I will remember the name, so. Okay, I remember you. Hi. No, that's okay. Yeah, there was a very expensive drink in a very expensive hotel lobby. Yes. And then the last one, oh no, yes. Okay, hi. Um, well, my name is Francis. Um, you can see my my slides or my PowerPoint presentation, and but you because I made some changes and I added some material. You can see the online version too. Yeah. Okay. It is readable. Okay. So my proposal is to go through the presentation, and then afterwards we can have a discussion and things like that. And well, and any point you can interrupt me if you want to, if there is any need for clarification. Um, so the title of the chapter, I guess, and also of the presentation, that's for sure, is Models for Residual Dependencies. And here is a short overview. Um, so in the meantime, between I sent the presentation to Mark for distribution, and now I have added some stuff. So there is more to be seen on the screen than there is in the handouts. But afterwards, I will send the updated version to Mark. So if you guys want it, you can have it then. So here is an overview. I will first start with an introduction and then talk a little bit about assessment of residual dependencies, but that's a very idiosyncratic part because I will only talk about some graphical procedures to assess residual dependencies and not about the standard techniques like, for instance, the Q tree measure and so on. And then I will discuss some models for residual dependencies, and there will be 4 models, types of models that will play a role. Sum score models, conditional models, random effects models, and marginal models. So here is the introduction. As you all know, in IRT, you have responses that come from the same person, and they tend to be more alike than responses from different persons. So that creates a kind of dependency due to the fact that responses are clustered within persons. And one function or one role of the latent trait or the random effect is to take into account that within person dependency, to capture that within person dependency. But a crucial assumption is that after you have accounted for the within person dependency with a random effect, there is local stochastic independence. So the responses to the several items are independent. It is also called in statistics more often conditional independence. But sometimes, unfortunately, this one random effect, or if you have a multidimensional model, these several random effects are not sufficient. Sometimes you are left with residual dependencies after you have taken into account this latent trait. And common examples of this are, for instance, tests that are based on reading paragraphs, where each paragraph is followed by several questions. The responses to the questions that pertain to a single, to the same paragraph, or tend to be associated more strongly than responses that come from items pertaining to different paragraphs. So items sharing a reading passage probably will show residual dependencies. Another example might be if learning takes place while you take the test. If that is the case, then a single latent trait is probably not sufficient to capture all the dependency between the responses. I will somewhat abuse the terminology in the field, and I will call all items that cluster together and that show residual dependencies, I will call them all item bundles or testlets. So for instance, if you have a reading paragraph, the items that follow that reading paragraph and possibly show residual dependency will be called an item bundle or a testlet by me. And the assumption is that within such a testlet there is a violation of conditional independence, but between testlets conditional independence still holds, and also outside the testlet there is conditional independence. Throughout my presentation I will focus on two examples, and one example is one that should be fairly familiar to you. That's the verbal aggression data set, and another one are what I call law data. So verbal aggression data, here is a short overview. 316 persons filled in a behavioral questionnaire. I guess it should be filled out actually, on verbal aggression, and there were 24 items, all of the same type. And here's an example: a bus fails to stop for me, I would curse. And then the participants in the study could answer with no, perhaps, and yes, and no was coded as 0, perhaps as 1, and yes as 2. But we will only look at the dichotomized versions of the data. So a no response will be scored as 0, and perhaps and yes are taken together, and they will be scored as 1. So that's the first data set. The second data set are the law data, and there are 441 high school students that were questioned because they were interested, or they showed interest in studying law. They got several texts to read, but I will focus on the analysis of items that follow one text, and that is a text on the president and the separation of powers in the United States, which happens to be relevant nowadays. But the test was taken, I think, 6 years ago. The text was followed by 6 questions, so it is actually a very small test of 6 questions, and they were also multiple choice questions. However, I ignored the fact that they were multiple choice questions for analyzing these data. I just pretended as if they were regular, normal items, and did not take into account the fact that people might also guess. This is probably not the best thing to do if you would, if it was a real analysis, but for this example, I don't think it makes a huge difference. Here is the first part, the assessment of residual dependencies. Before going to the modeling stage, you first want to find out whether there are any residual dependencies, of course. So what I did is I fitted a Rasch model to both the data sets, and that's where the Rush model is probably not the appropriate model for the law data. And then the question is, how can we detect such residual dependencies? Well, the procedure I followed, and it's also described in chapter 10 of the book, is I computed empirical log pairwise odds ratios. So for each pair of items, I constructed a 2x2 table. I looked at how many people had a 1-1 response on both items, how many people had a 0-0 response on both items, a 1-0 and a 0-1 response. And I computed the pairwise odds ratio and then took the log. So actually the formula is not correct. There should be a log in front of the equation there because it's a log odds ratio. This is just the odds ratio. The 0.5 frequencies are added because some frequencies can be 0, and especially in the denominator that can cause trouble, but also in the numerator if you take the log, of course. Then I constructed a grayscale matrix representing the magnitude of the log odds ratios. And the next step is I simulated artificial data based on the fitted Rash model according to the same. So I fitted the Rash model, took the parameter estimates, simulated new data, and for these new simulated data sets, I repeated the procedure of constructing the grayscale matrix based on the log odds ratios. And then I compared the empirical, or the one that was based on the observed data, with the ones based on the simulated data. So here is an example of how I did it. First, for the verbal aggression data, let's go immediately to this slide. It's also on page, let me see, which page? Page 293 of the book. So the top row is just the empirical log odds ratios between all possible pairs of items. And in the left column, there is always the observed, so the grayscale matrix based on the observed data, and in the right column, the grayscale matrix is based on replicated data. And in this case, I just I simulated 4 new data sets, 4 replicated data sets, and constructed these grayscale matrices. So I only showed the upper diagonal part of the grayscale matrix because the empirical log odds ratios are symmetric. So the lower part would be exactly will be the mirror of the upper diagonal part. So there is no need to present that because it's only redundant information. And from comparing what has been observed or what has been constructed based on the observed data and what has been constructed based on the replicated data, you can draw inferences with respect to how adequate the model is. So if the observed grayscale matrices look as or have the same characteristics as the replicated ones, then that indicates that the model is probably doing a good job. So if you would lose the labels, if you would not know which one is the observed and which one are the replicated ones, if the model is fitting adequately, you would not be able to pick out the observed ones. That is the idea. It's the same thing as with a classical numerical test statistic that is compared to a reference distribution. There, the comparison is done in numerical terms, but it's also the case that a test is declared significant if the numerical value of the test statistic stands out from the reference distribution. And this is the same. The replicated grayscale matrices constitute a kind of graphical reference distribution for a test statistic, and the test statistic is the observed grayscale matrix. So is this more or less clear in this explanation? So if you now look at the top row of the ones I have put on in the PowerPoint presentation, that is the pairwise log odds empirical or the pairwise log-odds ratio between each possible pair of items. So in the verbal aggression data set, there were 24 items. So you can compute how many pairs there are. You see that the observed grayscale matrix somewhat deviates from the replicated ones. In the observed ones, there tend to be darker spots than in the replicated ones. So it seems to be the case that the replicated or the observed association is larger than the replicated ones based on the Rasch model. Since there is in the verbal aggression data, there is a structure, so there are not just 24 items, there are also these item properties. You can also look at the association between responses, let's say, pertaining to the same item or to different items. So if you look at the bottom row of the depicted grayscale matrices, I have taken the average empirical log-odds ratio for items belonging to the same or different situations. So here is the explanation. First, the first element is the average association between all items pertaining to the bus situation. If you then go to the element first row, second column, these are associations between items, average associations between items belonging on the one hand to the bus situation and items on the other hand that belong to the train situation. And the element, the next diagonal element, the 2-2 element, is the average association between all items belonging to the train situation, and so on. So what you then see is that elements on the diagonal, so the average association between items belonging to the same situation, these elements tend to be darker than off-diagonal elements. Which means that items, if you look at the average association between items belonging to the same situation, that average association is larger than the average association between items belonging to different situations. And also that fact that items that belong to the same situation tend to be associated more strongly than items belonging to different situations. Also, that fact is not captured by the Rasch model, because if you compare the observed grayscale matrix to the replicated ones, well, the replicated ones do not have that clear, darker diagonal structure. I wonder, are these grayscale matrices? Are they? Can you see them very well? Is the quality good enough? Okay. So the middle row is constructed according to the same principle. The only difference is that the item properties based on which it is, or the item properties that you see there differ. So for the middle row, I've first computed the average for, let's say, for the diagonal elements. For the first diagonal element, I computed the average association between all items pertaining to the want to curse items. The second diagonal element is the average association between all items referring to the want to scold properties, and so on. So there are 6 diagonal elements and then a bunch of off-diagonal elements that reflect the association between, let's say, the cell 1, 1, 5 is the average association between items, the set of items that belongs to want to curse properties on the one hand, and on the other hand to scold properties. And then you also see for this observed grayscale matrix that there is a a darker pattern on the diagonal, meaning that the average association between items that have the same item properties is larger than items that do not have the same item properties. And this is neither captured by the Rasch model, because if you look at the replicated grayscale matrices, sometimes there appear darker elements, but they appear in a random fashion. So the Rasch model is clearly not capturing all the association that is present in the verbal aggression dataset. That is the basic message we get from this analysis. Is that more or less clear for everyone? If not, please do not hesitate to interrupt me and to ask me questions. So then I did the same thing for the law data, where there were only 5 items, and now I have a kind of a task for you, or a question for you. I want to test the power of these graphical methods. And so what you see here on this first slide with all these grayscale matrices is the situation I referred to before. So I lost the labels of which ones were the replicated grayscale matrices and which ones were the observed. Which one is the observed one? So now it's up to you to pick out the outlying well, the possibly outlying one. So there are 2 questions. Is there an outlying grayscale matrix visible? And if so, which one is it? Yes? Upright, that's this one. So are there other suggestions? This one, top left. Well, this was actually a joke because they're all based on simulations from the Rasch model. So there is no additional dependency, and there are no observed data in this one. So the people who said that there was an outlying one made a type 1 error. And then the second page, do you see an outlying one now? So any suggestions? Yes, that's the one from the observed data. The other ones are all based on replications replicated data sets simulated using the estimated Rasch model or the fitted Rasch model from the data. And in the second row, third column, that grayscale matrix is indeed based on the observed data. And there you see that between items 1 and 6, there tends to be more association than can be explained or can be replicated, so to speak, by the Rasch model. And possibly the same for items, the association between items 4 and 5. There also tends to be less association between items 2 and 6, but that is, that is a very light gray spot there. But here is the conclusion from all of this. That is, for the verbal aggression data, as we have said, there are larger correlations between items that share similar properties, like items that pertain to the same situation or items that have the same item properties. And for the law data, there seem to be problems with the association between items 1 and 6 and items 4 and 5. And for the law data, that has been confirmed by other methods as well, so not only by this graphical assessment. So these are clearly two data sets where we do find residual dependencies. The one latent trait proposed by the Rasch model cannot account for all the dependencies that are in the data. If you subtract that latent trait, if you take it into account, you still see clearly a pattern of association in the observed data that deviates from what should be predicted by the Rasch model. So here are now solutions if you're confronted with this problem, models for residual dependencies. So the basic model where we start from, as I said already, is the Rasch model. So everything what I talk about will be conditional on the presence of that latent trait theta p. Also, this is a repetition. The group of items that show residual dependencies will be called a testlet or an item bundle, if you want. A third thing to mention from the start is that not all approaches that try to account for residual dependencies have the same goal. Sometimes people are really interested in these residual dependencies. For instance, if you think there is learning in the test, you might want to model that learning process and you might want to learn something from it, try to predict it and so on. So there is a real interest in the origin of the dependencies. On the other hand, sometimes dependencies are seen as a nuisance. If you're, let's say, work for a test company and you want to make inferences, you want to measure people, you don't want your measurements to be made invalid by the fact that there are residual dependencies floating around in your data. So in that case, they're a nuisance, these dependencies, and you just want to take them into account in order not to disturb your measurement or inference process. Here is some notation. I will talk about capital P persons, and there is an index small p that runs from 1 to capital P. There will be capital I items and an index small I that runs from 1 to big I. And then the probability that a person P responds Y on item I will be denoted as has been indicated here below. So as I said before, there are 4 classes of models, or 4 families. There are sum score models, conditional models, random effects models, and marginal models. And again, note that everything is conditional on an already present random effect. That is important to note because if you look at the statistical literature, the same type of models will show up. but they're used to explain association in the data without first taking into account or without first introducing a random effect. So that's the reason why I mentioned this. So sum score models are the simplest one. What you do is, if you have a set of items that possibly show residual dependencies, you just take the sum of those items and you model that sum as a polytomous item. It has the advantage that it's very easy to implement. You can handle a moderate number of items, because if you have, let's say, 5 items, you only have 6, you need only 6 categories, 0, 1, 2, 3, 4, 5. So you can handle the association between 5 items. But there are also main or important disadvantages to this method. That is that there is a considerable information loss. Several different response patterns will be mapped onto the same sum score. So if you have 5 items, all possible response patterns with 3 items correct and 2 wrong will be mapped onto the response category 3. So you lose information. And also the parameters of the model will be hard to interpret, because they do not refer to separate items, but to this artificially constructed new item, this sum score item. So this is not the most appropriate model. Another type of model is what I call conditional models, and the basic feature of these conditional models is that in order to find the probability of a certain response on an item, you condition on the responses of several other items. So you condition upon the other responses in a testlet. And there are 2 main classes of conditional models, the so-called recursive and non-recursive ones, and this is a terminology that has been borrowed from structural equation modeling. So first, the recursive models. In the recursive models, you assume there is a kind of a priori ordering, and that is, for instance, if you think that there is learning in the test, and you start with item 1 and then to item 2 and then to item 3, there is a kind of ordering that is present. The recursive models demand that there is at least one exogenous item, so at least one item for which you do not condition upon the responses of the other items, and that there are no feedback loops in the model. I will explain that later. So here is an example of a recursive model for the case of only 2 items. So I assume that the ordering is first item 1 and then item 2. So for item 1, the probability formula is actually a Rasch model. It's a very common model. And then for the second item, the probability is conditioned upon the response that has been given to the first item. So then you see that in the probability equation there appears a term where parameter delta is multiplied by the response given to the first item. So if that response, we're only talking about binary items, if that response was correct, then yp1 is 1, so there appears a delta, and if it was incorrect, the delta disappears, because then it will be multiplied by 0. So this allows for modeling learning, because if the delta is, for instance, negative, and that means that in the case you respond correctly to the first item, the second item becomes easier, because something is subtracted from if the delta is positive, then something is subtracted from the difficulty parameter, and that means that learning takes place because the item becomes easier. With respect to the interpretation of this model and its parameters, delta is easily interpreted as a learning parameter. And it is related to the odds ratio. I'm not going to discuss that in detail. If you want to know more about it, you can look at the chapter in the book and the references therein where that has been explained. And another point of interpretation, and that is something I want to stress throughout this presentation, is that there is no reproducibility in this model. And what that means is the following. So why no reproducibility? Well, in this recursive model for the first item, we have a Rasch model. That's fine. We all want to work with Rasch models. We know that the item parameters, the betas in the Rasch model, are easily interpreted as difficulty parameters. Rasch models have these logistic curves. So we want to work with Rasch models. And for the first item, that's fine. We have a Rasch model. For the second item, however, if you compute the marginal probability of responding correct to this second item, you have to apply the law of total probability, because we only defined the conditional probability of a response to that second item, so conditional on the response to the first item. So we have to multiply and the conditional probabilities by the marginal probabilities of a response to item 1, and then sum all possible outcomes for that item 1, and then you find that the marginal probability of that second item is no longer a Rasch model. In effect, it strongly, well, the formula is certainly not a logistic equation anymore, and the parameters are very hard to interpret. So the beta 2 parameter is, in this case, cannot be interpreted as, for instance, the difficulty of the second item. You actually see that the marginal probability of responding correctly to this second item is influenced also by the difficulty parameter of the first item. It is influenced by the learning parameter and by the beta 2. So that's what I want to say by the fact that there is no reproducibility. If you work with this kind of conditional models, the marginal probabilities of giving a certain response or giving a correct response to the items are no longer Rasch models. And the nice interpretation of the parameters that come with the Rasch model is lost. Here I copied some equations from the book, and it is only to focus your attention on the fact that the formulation of the model can be much more general than what I have done before. And the point is that you start by writing the joint probability of a certain response pattern as the marginal probability for the first item of a response on the first item times the conditional probability of a response on the second item given the response on the first item, and so on. So you have this sequential decomposition, and then the logit of the probabilities of responding correct on item, the logit of the probability of responding correct on item I given all previous responses is then written as this linear function. And you have then this predictor or design matrix W, which contains the responses to all the previous items and also products of responses. And that can be used to model the association. And here are examples of this W matrix. So you can condition on the sum score of the previous responses. So that is an easy way to model, let's say, learning. The more correct responses you have given to all the previous items can have an influence on the difficulty of the item you're currently responding to, and so on. So that's the first specification of the W that is shown there. So that was a recursive model where there was an a priori ordering in the items. For the example, for instance, where you have a reading paragraph that is followed by several questions, there is no a priori ordering among the items, nor there is an a priori order, for instance, in the verbal aggression data set. Items cluster together for some reason or another, but not because you learn throughout taking the test. In such cases, a non-recursive model, or what you can call a non-recursive model, is probably more suitable. And here is an example, again, for the simple case of two items. So what you define is a joint probability of a certain response pattern for the two items, so YP1 and YP2, and that joint probability looks as follows. This is a conditional model because the conditional probabilities of a certain response on item I given a response on item J is a Rasch model. So starting with this joint probability formula, the conditional probabilities are all Rasch models. And again, the delta is a dependency parameter, and that is related to the odds ratio. And again, as a disadvantage to me, there is no reproducibility. So for none of the items involved in this dependency relation here, so we have here an example with two items. Well, for none of these two items, the marginal probabilities are Rasch models. The marginal probabilities are something much more complicated than Rasch models. They can mimic Rasch models in some cases, but the interpretation that you can attach to the beta parameters is not one of a single difficulty. So again, you see that the marginal probability of, for instance, responding correct to the first item is influenced also by the difficulty or the beta parameter pertaining to the second item, and also by the association parameter. And here I copied again the more general equations that are also given in the book. So you start by defining all conditional probabilities of responding correct on item I given the responses to the other items in the testlet, and these are defined as Rasch models, and from that you can derive the joint probabilities of certain response patterns. A nice thing of these non-recursive models is that for estimating them, you can reformulate the models as a model for polytomous items or for a single polytomous item. So if you have, for instance, two binary items that are that will be modeled by a non-recursive model, you can look at it as if it was one virtual item with four item categories. With four categories, a 0 category corresponding to the 0-0 response, category 1 corresponding to the 1-0 response, category 2 to the 0-1 response, and category 3 to the 1-1 response. And here, and that's also copied from the book, I show how you can reformulate these, it's a non-recursive model, as a model for a polytomous item in the case of two items in the testlet. As a kind of exercise with respect to these law data, I fitted, so the law data had 6 items, so there is beta 1 up to beta 6. There is one sigma that corresponds to the variability or the standard deviation of the latent trait distribution. And so I fitted first the Rasch model, and in the first column you find the estimates for the Rasch model and also the AIC for that fit. And then in a second column I fitted a residual dependency model, and it was the non-recursive model I talked about before. And the residual dependency was between items 1 and 6 because they showed the strongest dependency. So we introduce a parameter beta16 that it's actually the same as the delta in the previous equations, but here I added the subscript to make the point that it's for the association between items 1 and 6. And then you can see how the estimates of beta 1 and beta 6 change in comparison with the Rasch model. Also, you see that the AIC is going down for the residual dependency model compared to the Rasch model, meaning that there is indeed residual dependency between items 1 and 6 that has been modeled now. Okay, so we already discussed some score models. Then we discussed conditional models where you write the conditional probability of giving a certain response on the responses given to other items. Here is a third approach to model residual dependencies, and that is the random effects approach. So it is just an extension of what has been done before. What you do is you add a testlet specific dimension. You add for each possible testlet in the data set, you add a new latent trait, and that has been denoted here by this round theta. So all items that are involved in the testlet get this round theta p in their probability formula. And then so you have now actually a two-dimensional model, and it is assumed that the two latent traits follow a bivariate normal distribution. And so you can estimate the variances of these latent trait distributions. So with respect to the interpretation, if you want to interpret the dependency between items, you have to resort to person-dependent odds ratios. That's less important now. And with respect to the reproducibility issue I talked about before, also in this case you do not have reproducibility. So the marginal probability of giving a correct response to item I, and by marginal probability I mean the probability that depends on the single latent trait, or that is conditioned on the single latent trait, the theta p you're interested in, the one you want to measure. Well, this probability is not a Rasch model because you have to integrate out the other theta p, the one that is the testlet or refers to the testlet specific dimension. And because this logistic normal integral is not a logistic function, it is impossible to arrive again at a Rasch model. I also applied this random effects testlet model to the verbal aggression data. And because there is this multitude of possible testlets in these data, because of the fact that a lot of the that there are a lot of item properties that are present in the data and that are also overlapping, I opted for a 10-dimensional model. So it's a very big model, and I included random effects for behavior types, for the 4 situations, for the behavior modes, want and do, but not for the situation type. So self-blame versus other blame was still a fixed effect predictor. So if you add the number of random effects, so 3 for the behavior types, curse, scold, and shout, it should be, 4 for the situations, bus, trains,